Hello everyone. Today I'm going to be essentially deriving the arc length formula utilizing calculus, and then subsequently what I'm going to do is I'm going to prove that theorem to you utilizing a calculus-based problem. Okay, so the arc length is described as a function with a specific arc length that we want to calculate. So t of 0 we'll assign these values to, and t of 1. So this is essentially a, and this is b. Okay? And this is a function, so f of x, from t of 0 to t of 1. So the starting value to the subsequent value, or the ending value, I should say. And this is the x-axis, this is the y-axis, evidently. So now what we can do is, I see a very familiar geometrical shape now. If we pick any point, which I'm going to pick here, we want to calculate this arc length specifically of the function, of the entire function. And I see that it formulates a significant geometrical feature, which is a right triangle. Now with this right triangle, we can derive the arc length formula, because now I see a change in y and a change in x. So the change in y denotes the vertical axis, and the change in x denotes the horizontal axis. So the change in y over the change in x, well, that's simply the slope, which is the derivative. So the derivative is the slope of a certain function. So now if I take into consideration the Pythagorean theorem, a squared plus b squared equals c squared, we can state that a equals delta x and b equals delta y. So the change in y over the change in x. That's Newton's notation. There's another notation I'll describe a bit later in the video, but for now we'll just call it delta x and delta y, so Newton's notation. So now if I incorporate delta x and delta y into the equation, or the theorem, so delta x, and that's going to be with respect to t, because this is an additional variable that we want to take respect to. So delta x over delta t squared plus, and we're trying to calculate c, which is our resultant vector in vector calculus. So the resultant vector is simply c, or the hypotenuse of this specific right triangle. So right now we're just trying to find c at this moment in time. So then we also have delta y squared over delta t squared. Or sorry, these wouldn't be squared yet, but yeah, if we do theoretically do that now, if we simply use simple exponent rules to distribute, we would get delta y squared over delta t squared, which is equivalent to c. Now that I have that information, sorry, c squared, I can now square both sides. Now by squaring both sides, I find that c equals the square root of delta x squared over delta t squared, distributing the exponents, and delta y squared, plus delta y squared over delta t squared with respect to delta t. I'm not going to write delta t yet because that's going to be later. So that's equivalent to c at the moment in time. So what I want to do now is, if I take the summation from n equals 1 to the nth term, or simply n equals 1, the starting position, to the nth term, the ending position, of the function f of x, so the square root, the arc length formula, of delta x squared over delta t squared plus delta y squared over delta t squared, with respect to delta t, I find that we need a little bit more information, because now I want to approximate this area. I want to approximate the arc length of that specific arc, or of the function that is assigned to these two values. So this would be t of 0, and this is t of 1. And this should just be a, because these are the two values, the initial position and the ending position. So what I'm essentially doing is I'm taking these minuscule tangent lines on the arc length, and I'm approximating them up to infinity. I'll get to that in a moment, because now, if I do take those into consideration, those little slopes, I'm going to approach infinity to make more of a precise calculation and more of a precise approximation for that arc length. So if I take the limit as n approaches infinity, all those little tangent lines as they approach infinity, I find an interesting resolution here, because now, I should say solution, this summation sign now turns into an integral sign from a to b. Essentially what it's doing is it's essentially being stretched, right? We're stretching the amount of area, right? So this, as n approaches infinity, these slopes become more infinite, and now we can approximate the arc length even better, more accurately. Of the function delta x squared over delta t squared plus delta y squared over delta t squared. And this should not be in Newton's notation anymore, because now we moved on to a different notation, which is Leibniz's notation with respect to t. So with Leibniz's notation now, this is an integral sign, so now we can utilize integration. So it's no longer Newton's notation, it's now Leibniz's notation, which is, he was another brilliant mathematician, just like Isaac Newton. Okay, so now we can also take into consideration that a equals t of 0 and b equals t of 1. And that is the arc length formula. So now what I want to do is I want to prove that this formula is valid for certain calculus-based situations for finding arc lengths. So now if I take into consideration the unit circle, 0, pi over 2, pi, and then 3 pi over 2. I can keep going on and on, but I'm not going to bore you with that. This will be 2 pi if we just keep going in a counterclockwise position continuously. Let's say I want to calculate the arc length from 0 to pi over 2. Well, evidently, we know the arc length of that is going to be pi over 2. But I just want to prove that that solution will come out in this equation, or this formula, I should say, that I derived. So we know the starting value of t of 0 is equivalent to 0, and t of 1 equals pi over 2. The starting position, the ending position. And now we have the square root of dx over dt plus dy over dt squared with respect to t. So now we can essentially parameterize, right? Because now we have x equals the cosine of theta and y equals the sine of theta. Just like if you take a right triangle and we draw that, we can now calculate x and y values using sine theta and cosine theta, because the x value is cosine theta because the adjacent over the hypotenuse is going to be on the horizontal axis, and the sine theta is opposite over hypotenuse, which is going to be on the vertical axis or the y-axis. These really should be converted into, so x equals cosine of t, because this is with respect to t, and y equals the sine of t, because it's with respect to t. And now what I can do is I can take the derivative, because now we have dx over dt, and we have, which we don't know yet, and we have dy over dt, which we don't know yet. Now dx over dt is simply d over dt of the cosine of t, because that's equivalent to x. So the cosine of t, the derivative of the cosine of t, is simply negative sine of t. And d over dt of sine of t is equivalent to cosine of t. Okay? So now, if we take t of 0, which is 0, so assigning these values and integrating these values inside of the integral, or the integrand, I should say, and t of 1 is pi over 2, the square root of, we have dx squared over dt squared. So essentially, dx squared over dt squared is equivalent to negative sine of t squared, which is sine squared of t. So what we get now is we get sine squared of t for our dx function, dx, so the derivative of with respect to x. And now we have dy squared over dt squared, which is equivalent to the cosine of t squared, which is also known as cosine squared t. So plus cosine squared t with respect to t. I'm going to bring this over here so we have 0 to pi over 2, the square root of the sine squared t plus the cosine squared t. Now many of you may recognize this, the Pythagorean identity. And the Pythagorean identity, this is what makes it so beautiful, because the Pythagorean identity is sine squared theta plus, or any function, any variable, plus cosine squared theta, which is equivalent to 1. So we get 0 to pi over 2 of the square root of 1 with respect to t. Now the integral of the square root of 1, so now we can simply simplify this. We get 0 to pi over 2 of 1, square root of 1 is 1, with respect to t. We now get this, the antiderivative of 1 is, with respect to the variable t, is t, from 0 to pi over 2 as our limits of integration. So now we get t, so we get pi over 2 minus 0, which is pi over 2, which is the arc length of that arc. 0 to pi over 2 is pi over 2. There is the proof. And that was an exciting one there. I hope you all enjoyed. That was an interesting one. And I hope you learned a lot. Comment down below if you want more videos like this of derivations, or simply just calculations of random things in calculus, or physics, or chemistry. All right, thank you so much, and have a wonderful day.